I'm Robert Sutton and this is my robot. In this video I'm going to discuss the hardware that I've used on the robot and some of the reasons why I chose that particular hardware and how also it's connected together. The robot consists of a Roomba 630, an RP LiDAR, a Raspberry Pi, which is in the case here, and a battery. So first things first, the battery. So the battery is identical to this one here, which is a typical battery bank that you use for a mobile phone or a tablet when you're away from mains power. It supplies 10 amp hours at 5 volts, which powers the RP LiDAR and the Raspberry Pi. It seems to be able to supply a good 3 or 4 hours worth of runtime. Next is the Raspberry Pi, which lives over here in this box. This is a similar Raspberry Pi, slightly older model, you've probably seen before. It's responsible for communicating with the RP LiDAR, the Roomba, and also a laptop via Wi-Fi. The Raspberry Pi collects data from the Roomba and also issues commands to it, and also collects the data from the RP LiDAR. It's also responsible for some low-level crash avoidance, taking data from the bump sensor on the Roomba and also from the LiDAR, so that should the robot stray too close to something, it will actually stop it independent of what the laptop may be thinking about the situation. I'll just take a moment to mention the Wi-Fi. This particularly large antenna I have here. I did start off with a small USB dongle that was quite inadequate basically. Anytime I'd invite a few friends into the house, the extra interference they created would cause my Roomba to lose communication, so I went for a much larger antenna and has much more consistent communication results. So the LiDAR. This is our RP LiDAR up here. The top part of it spins and it scans around in 360 degrees in a plane, taking measurements at all points at about 1.5 degree intervals. Obviously it's a plane, so things that are either below that or above it can't see, but anything on that plane it sees, leaving the robot a little vulnerable to low obstacles like shoes that are left around or things that are high for that matter that it may clip, for example on the antenna, that are above the plane that the LiDAR can detect. All of the hardware is housed in this wooden assembly, which has got a few 3D printed parts here and there that hold it together. We've got a ball and socket set up here, which are also 3D printed so that it snaps onto the robot and off as need be. They are held in place with double-sided tape, as are most of the other parts. The battery, the RP, Raspberry Pi and the RP LiDAR all hold down with double-sided tape. So the Roomba provides telemetry data, that is the distance it's travelled and the angle that it's turned, to the Raspberry Pi, which in turn sends that data onto a laptop. The Raspberry Pi also issues commands to the Roomba in terms of what speed to travel at, for example 20 centimeters per second, and also what radius to turn around. So you would, for example, say turn along a 2 meter radius, forming a nice curve. The Roomba also provides data about collision via the bumper, which gets fed to the Raspberry Pi and back to the laptop, as well as the Raspberry Pi immediately stopping should it detect such a crash. Right, so I'll just run you through booting up the whole system. First I'll power on the Roomba. I've got a green light here. Plug the Raspberry Pi into the battery, and that's powering on. So the first thing that you'll notice is that the RP LiDAR will power up, which will start spinning in a few seconds. There we go. The software on the Raspberry Pi is now starting up, and first thing it will do is reset the RP LiDAR. So it stops spinning in a moment, the reset will be complete and it'll start spinning again. The software goes through some network setup and trying to communicate with the laptop. Once that's done, it will then proceed to take control of the Roomba, which with the lights across here, the front here, will change to red and we'll get a beep or two. There we go. So the Raspberry Pi is now in control of the Roomba and receiving data from the RP LiDAR. So the software is still doing a little bit of initialization, searching for the laptop, which it's not going to find. But once that's done, it will be fully responsive. Now I can demonstrate that the LiDAR is putting out its plane of scan data and that the Raspberry Pi on board is reacting to that. So back here it doesn't care about anything, but if something gets within 30 centimeters at the front, You can hear the audible alarm that we have. But that also, if it were receiving commands to drive from the laptop, for example, it would just simply ignore them once something comes into that range. So you see that's about 50 centimetres there. It's about 5 centimetres out to the side. If we're travelling down a hallway or something, we want to get nice and close to the walls, but we don't want to run into something directly in front. So that's the code there also ignores things inside the Roomba's radius. So I can run my hand around here and nothing happens, but if I step out a little bit, it detects it. So it's how the system ignores for example, the Wi-Fi antenna, which is technically inside the radius, but so. Right, and just to demonstrate that it is a plane, I can run my hands around here and nothing, or I can do them up here as well, nothing, but if I come into that plane, you can see that it's detecting my hand directly in front of the LiDAR. So a little bit of information about the LiDAR. It spins about 6 times a second in its current configuration, taking 2,000 measurements per second. So it's quite a lot of data to be processed. So because of the limitations of the LiDAR being a plane and obviously small objects in front of the robot are not seen, I am intending to install a Orbeck Astra Pro on it. I have 3D printed this mount which will allow it to sit right at the front where I'll be able to see things immediately in front of the robot. So I'll just move that aside for now. So I'm going to take a minute to talk about LiDAR and why I've come to using RP LiDAR and a bit of backstory there. I started playing out with sonar and infrared sensors, and you can see just sitting here is my previous LiDAR system, which consists of a LiDAR light, which is up here. We have a nice big stepper motor down the bottom which spins this mirror, and this was able to spin at about 1 revolution a second, taking 100 data points per second. But the problems I ran into that were obviously not a lot of data coming in, only 100 data points a second compared to 2,000. Also, the straight lines started to become curved as I pushed up the sample speeds. The LiDAR light, I believe, averages ranges, so as it's moving along a wall and the range changes, we get some averaging and the wall gets distorted. You get curved walls instead of straight walls, which is not particularly useful. One of the other interesting little problems that I encountered with this particular build is I run everything out of Java, and because Java is not a real-time programming language, I was stepping the stepper motor, but if you exceed the stopping speed of the stepper motor, every now and then Java will pause for a garbage collection, the stepper motor will sail on just through momentum, and then we've lost our position. We no longer know which way the mirror is facing. So given that I was using a non-real-time programming language, I couldn't exceed my 1 revolution a second, and there was also of course the problem of lines becoming curved just because of the sample rate of the LiDAR device there. So this led me ultimately to buy the RP LiDAR, which ultimately I wish I'd done a long time ago, because I mean obviously this didn't come cheaply and I still had to end up buying this. So could have been some money saved had I gone straight to a device like this, which is known to work. I was also going to talk briefly about gyros, and the problem I found with these cheap gyros is that they have jitter, which is not that big a problem. We can just average our data out, not a great problem, but what they suffer is continuous drift. I typically found, even with quite a warm-up period and initialization and averaging, and that I would still end up with somewhere around a 1 degree drift per minute. So in a 10-minute trip, the angle coming out of the gyro is 10 degrees out, and also you would get occasional jumps where the gyro would suddenly jump 25 degrees or something. So the gyro actually is more misleading than useful for most of my uses. I also talk about compasses. This is either a gyro or a compass. They look pretty similar. And inside the house, compasses are really quite problematic. Probably one of the most extreme examples of that is as my robot was driving down a hallway in a nice, actually straight line past a fridge, and as it approached the fridge, it should have driven straight past it, but it simply curved towards it as the compass heading changed as it came past this large metal object. And at one stage I did see where my gyro was kind of behind the fridge, actually through a wall behind the fridge. And I was watching the data and I could see the compass heading jumping alternately about 90 degrees at about 50 hertz. Obviously I couldn't read the data that fast, but looking back through the logs I could see the data jumping at around 50 hertz, through a 90 degrees shift, which is completely useless and, as I said, has run my robot into walls. So I neither use gyros nor compasses anymore. My previous robot was based on a Rover 5 platform, which is a four-wheel tracked platform, is the default configuration there. And I had been working on this for a very long time before I discovered that when a tracked vehicle turns, that it doesn't pivot around its centre, or at least in most of the cases in my particular configuration, it would turn around one end of one track, and that would usually vary depending on which way it's turning and what surface it's on. It basically meant that you couldn't take the telemetry coming back from the encoders on the wheels to give you any useful positional information or heading information for that matter, because depending on what point it happened to pivot around, the angle would be quite different, as would the position. I wanted to take a minute to talk about servos. Now this is a continuous rotation servo, which was in one of the very early variants of my robot. And two things I learnt the hard way about that is, one, that these analog servos, you need to drive the PWM at about 25 to 30 hertz. I was running mine at about 300 hertz. And the net result of that is the servo got hot enough to melt itself. Without going into how the electronics inside the servo works, just needless to say that you need to run your PWM at 25 to 30 hertz or you'll destroy a servo. The other interesting thing about this is a continuous rotation servo, and while you might think, great, I've got an Adreno with 12 bits of PWM, gives me 1,000 increments of control, it's actually not how the PWM drives the servo. Out of that you probably get somewhere around 200 steps of control on a normal servo, but when you move to continuous rotation, what you get is probably about 4 or 5 steps of speed control forward and 4 or 5 steps of speed control backwards. So it's very granular control over the servo. You go from stationary to full speed forward or full speed backwards, and not much in between. You also don't have actual speed control at that point. You're actually controlling voltage to the motor, which doesn't give you either power or speed control. So it's a very poor way of controlling a wheel. And it's open loop as well, so you actually really don't know what's going on. And getting two servos to run at the same speed, which is not their maximum speed, turns out to be incredibly difficult. There's also one more thing I wanted to say about servos, is their repeatability is, in the small cheap ones, is certainly quite terrible. I was at one point sitting a sonar on top of a servo and moving it through an arc to build a picture of the space around me. And what I found is moving to a point from the right, say, as opposed to moving to that same point from the left, would actually be about 10 degrees, plus or minus 5 each way, different. So the repeatability was quite terrible and not particularly useful. The only way you get reasonably reliable data was to sweep your intervals from right and make a full sweep back and sweep your intervals from right again. If you did the back and forth process, your angles would be all over the place. I was also going to quickly mention my experiences with sonar. This is a sonar device that I was using, and they actually work pretty well until you get into a small room with hard walls and it's an echoey space, and then you find your robot sitting with a metre of clear space in front of it, but the sonar's reporting there's only, say, 30 centimetres in front of it. So I moved away from them as well, because they don't provide much data, and it can also be very misleading at times. Quick comment about the Roomba. When I first got it, its telemetry was off quite badly. I contacted Roomba and they very kindly sent me out this device to upgrade the firmware on the Roomba, and after applying that, things behaved much, much better. So one of the design choices here was all the devices here are all connected together via USB connectors, which is just really neat, tidy and easy. There's very little here in wiring, I mean a USB from the Raspberry Pi to the LiDAR, USB from the Raspberry Pi to the battery pack, and this is USB to serial down to the Roomba. So the Roomba provides telemetry from its two wheels, and it turns out that the data that comes back from the Roomba is really quite good quality. It's quite accurate. I have actually found though that the telemetry from the wheels, there's one shortcoming there, is when it's travelling less than about 2 centimetres a second, I don't believe I get any useful telemetry out of it, so I tend to keep my speeds above 2 centimetres per second. I picked up my Roomba second hand on eBay for $2, where it had a dead battery at the time, which I revived, so I'm still using that dead battery, but it is otherwise in good working order. So that's it for this week. Thanks for listening.